Tamamdır.
Önce kendini tanıt. Ondan sonra işte neler çalıştın, nerede staj yaptın. Ondan sonra konuna başla.
Okay. Can you see my screen?
Clearly.
Hi everyone, welcome. I'm Melek Efşan Çağlar and I'm a mechanical engineering student. I'm currently doing my internship on TUSAŞ Engine Industries in secondary air systems department. And today I'm going to present my thesis, which is on investigation of Labyrinth seal leakage with computational fluid dynamics. And my advisor is Assistant Professor Sedat Tokgöz. Considering I only have 15 minutes, I'm going to try to skip fast. So I'm not going to go into this. To start with, I have to mention the secondary air systems, which is the air systems that gas turbine engines include. And its main functions are cooling, sealing, and balancing the axial loads. And by means of sealing, we can say preventing the hot gas ingestion into rotor-stator cavities and bearing sump regions. And also it has anti-icing properties too. And the air that is used for these tasks are discharged from compressor, which is an expensive air, and it leads to a negative impact on overall efficiency to overuse it. So we have to manage those air systems really carefully. And in the figure, actually, this is just for you to see that it is discharged from the compressor. So in this manner, we have to control on these flow systems, and we use various sealing elements. Some of them minimizes parasitic leakage flows, and some of them just meters the cooling flows into the desired leakage rate. And as you can see in the figure, there are various types of sealing elements throughout the engine, and they provide sealing at different spots. And all of these aforementioned tasks shows us that sealing elements have an important role in engine performance, efficiency, and safety.
Efşan, why don't you use your mouse?
Okay. So I have mentioned that there are various sealing elements throughout the engine. We make our seal selections based on the type of fluid that is going to be sealed, the type of the relative motion that the surfaces that we are trying to have sealing on, the type of the relative motion in between them, level of sealing required, pressure levels, operating temperatures, expected life, and obviously ease of installation, removal, and manufacturing, and cost. And here we can see a guide that can lead us into the true seal. So my scope is on Labyrinth seals, which are dynamic non-contacting seals, which means that they allow the relative motion between stationary and moving components. Advantages of them consist of their simplicity, easier to manufacture, and with lower costs, and their reliability, that they can provide leakage under various operating conditions. There are obviously other types of seals, like carbon and brush seals, which may have better sealing characteristics, but design gets more complex and manufacturing becomes more expensive, and we have various sealing elements. So in this manner, I'm going to be investigating the Labyrinth seals. So my scope of this study was to investigate this both smooth land and honeycomb land Labyrinth seal leakage flow using computational fluid dynamics, and investigate the influence of selected parameters, which I'm going to mention later, and doing verification using the analytical expressions and experimental data from literature. And I have chosen 2 data sets. Labyrinth seals, I want to talk about the flow physics of labyrinth seals to give a better insight. As you can see in the figure, labyrinth seals provide a tortuous path to flow by a series of teeth, which act as orifices, and they work with the principle of rapid contractions and expansions. And when the flow comes from upstream and it jets out of this clearance gap, it expands into this cavity, and this expansion causes a flow recirculation, and this flow recirculation generates shear layers and destroys some of the dynamic pressure, which leads to a loss in total pressure, and this process continues in a series of teeth. The wall jet along this stator land suffers minimum from this phenomena, so it's almost become carried over into the next tooth, which is obviously undesirable for better sealing characteristics. So we can model the labyrinth seals with either thinking of it as a series of orifices with local pressure losses, like I mentioned, or as a rough pipe with uniform wall friction and frictional losses of fluid, which is more of a direct method rather than iterative, like this. And the analytical expressions that I use actually use this technique, but modeling as orifices gives a better insight into flow physics, so I'm going to be mentioning that with more details. You can see the details of the orifice model here. We can think of each tooth as a sudden expansion and contraction mechanism, and this will actually explain why geometric parameters matter. When the flow comes here and goes under a sudden contraction, if we think of this here as a tooth-tip thickness, which these tooth-tip, we can think of this, this length of the tooth-tip thickness will decide the characteristics of this recirculation here, and which will actually affect the effective area that we can use here, which will affect the seal leakage. If the recirculation zone is more long, then we will have a more bigger effective area, which will increase the leakage. So clearance, which is obvious, and the pitch where it affects is that when the sudden expansion mechanism happens, where the flow will impinge on the next tooth is dependent on the pitch between those two teeth. So those are all important parameters, and we all see those parameters in analytical models. And I want to talk about the design requirements of labyrinth seals. Obviously, we want effective pressure sealing between rotating and stationary surfaces with minimum leakage flow. This is the main task. It should have a minimal impact on overall efficiency. It should have acceptable generation of windage temperature rise across the seal, and acceptable impact into the rotor dynamics. And to fulfill those design requirements and improve the seal performance, we have to accurately predict the flow physics, and for which we need the information of key design parameters. So this is an important table from literature, from Tipton, key parameters. And as you can see, both geometric parameters and flow-related parameters have different type of influences on seal leakage, and the knowledge of this will make our designs better. However, this has a bit of a problematic side to it, because it's from literature. I couldn't change it, but clearance has a strong influence, and it has been shown with many studies, but it took it as moderate, so I have to warn about that. About the labyrinth seal geometries, as you can guess, there are different types of seal geometries, which are actually adapted for different conditions. Like for example, if it's angled, it can provide better sealing characteristics based on the direction of the flow. However, those actually depend. This actually depends on how if you have available space in your engine. And some of the design parameters that I mentioned here, like number of teeth angle, pitch to tip thickness, clearance, etc., we can see in this figure, so it can make better sense. Before I
Last 3 minutes.
Well, I have a lot of to tell. Oh my. Okay. So I have to say that clearances change during operation, and sometimes we can't work in the clearances that we want to, and honeycomb blends allow us to reduce the leakage mass flow rates in the same clearances dense unit configuration. My methodology was to construct the CFT model, gather verification data from literature and compare it, and if it was in the acceptable error levels, I would verify my model. And these are the analytical expressions from literature. And I have prepared an Excel sheet for my analytical calculations and made iterations. Those are my CFT model descriptions, but I won't probably have time to describe them. And for results, I used the experimental data represented by Stucker and analyzed those parameters that you see in this table: 3 clearance levels, 2 tip thickness levels, 2 pressure ratios, and 3 rotational speeds. And this is my mesh independency study for my model. As you can see, it doesn't change after a while. And I have to skip some of it. So these are actually my errors for mass flow rates, which are in acceptable levels due to the literature. And I want to talk about the parameters and how they affect, because I obviously have no time. So the effect of clearance, as you can see here, it is a very dominant parameter, and its leakage flow increases with increasing clearance, and it's valid for all pressure ratios. And you can see the effect of 2 tip thickness. Bigger 2 tip thicknesses leak more than smaller 2 tip thicknesses. Effect of pressure ratio, bigger pressure ratios leak more than smaller pressure ratios. Rotation decreases the leakage, but it has a really tiny influence. And for honeycomb reduction, I found 17% reduction for each one clearance and 7% for other. And those are my velocity contours, static pressure and total pressure controls. And for the other data set, I actually did the same procedure and found really acceptable error levels. And you can skip this. And at the end of the day, I found that at the clearance of 0.2, I have a really good agreement in mass flow. In all of the other parameters changing, it doesn't matter. At the clearance of 0.5, it was still good agreement, but not quite well as this. At the clearance of 0.1, my results deviated a bit much, but this is really small clearances and small numbers, so in proportion, even though it looks big, it's not that much of a mistake. And I have found that the clearance is the most dominant parameter that affects the Labyrinth seal leakage, and I have found that my mass flow reduction with honeycomb-induced mass flow reductions were in good agreement with literature, within 2% and 9%. And for the second data set by Yalçın and Doe et al., I also found really good agreement. And due to computational problems, my work plan was shifted. And so in upcoming months, which I continue my internship, I will try to investigate on more parameters. And I have put appendix for those who wonder. And those are my references. Thanks for listening.
Thank you, Efşan. Any questions? I have a question then. Efşan, have you considered temperature dependency, especially on the design geometry you are considering? Variation of geometry based on temperature?
I didn't really I wasn't really interested in temperature, but obviously I have compared my temperature levels to see if they were in the acceptable levels with the literature data, but I didn't do like a whole other study on that. But
all your analysis were in steady state, right?
Yes, they were all in steady state.
Okay. What turbulence models did you choose? K epsilon, KW, K omega, and?
Yeah, I didn't have time to explain it, but I have chosen K epsilon realizable and K omega SSC, but K omega SSC provided better solutions for my case. For swirling flows, K epsilon realizable provided better results, but for 2D analysis, SSC K omega I have used.
Okay. Any more questions? Thank you, Efşan. I think we have to move on. Onat?
Okay.
Yes. Is my voice clear?
Yes, we can hear you.
İlyas Hocam, can I make a comment?
Sure, go ahead, sir.
Efşan's study, and 2 weeks ago, TI chief engineer and his team of secondary flow will listen Efşan, and she has initiated a good modeling study since TEI is moving more larger and larger engineering engines design. I have one recommendation to Efşan, and that study in TEI will be studied further and further. As you said, temperature effect, different turbulence models, different clearances, and lots of different geometrical parameters. And I have one recommendation to Efşan. She has to do a master and PhD. And I hope she gets a job offer from TEI. She has to continue more academic study and has to continue on this topic further. This is the only recommendation I have for Efşan.
Thanks for your recommendation.
All right. Thank you, Lasucuğum.
Okay, thanks. Onat?
Yes, I'm sharing my screen. So can you see my screen?
Yes.
Okay, dear teachers and my dear friends, I'm Onat Altay and I'm a mechanical engineering student at Gebze Technical University. And I have done my internship at the AI's AIT Center, which is Assembly Integration and Test Center. And today I would like to present you my graduation project, which is designing and performing strength analysis and based on hand calculations of a nose landing gear fork of a trainer aircraft. And my project advisor is İlyas Kandemir. So in this project, I will mention about the key references that I use mostly. I will give a brief introduction about landing gears and fork and goals and steps of this project. And I will explain how did I achieve the scope of the project with methodology part. Although I have some missing points, I have achieved to design a C-sectional fork based on some assumptions. And finally, I will talk about what else can be added and show my references of the project. In my project, these are the key references that help me a lot to understand the concept and standards. Infante performed a failure analysis to a landing gear fork, which has failed because of fatigue. And Türkmen designed a whole landing gear and performed a computational strength analysis for Hürkuş Type C. And Raymer and Curry wrote a textbook about designing an aircraft. And there is also CS23, which is a standards and which is a certificate of standards that mentions about safety factors and landing and ground loads for light aircrafts. And Ahmet Ashtan from TAI's Technopark guided me for this project. And landing gear of an aircraft provides a safe landing since it damps the dynamic and static forces during landing. And also it allows ground movements like taxi. And designing a landing gear includes many departments to work together. And Federal Administration of Aviation states that 55% of aircraft's failures occur during takeoff and landing, and many high percent of this is because failure of fork, landing gear. And as you can see in figure 3 and 2, they are the forks. Let me open my pointer. And these are the forks of landing gears. So duty of a fork is to translating the ground and landing forces that are coming from the axle to the rest of the landing gears. So in figure 4, number 5 and this number 5 are forks. And forks suffer from fatigue because of high landing cycles. And that's why for human safety, fork must be very rugged and have high strength fatigue resistance. Infante performed a microscopic fracture analysis to a deformed fork, and he finds out that a crack propagates starting from the bolt holes to whole fork surface. And this failure took place after more than 17 landing cycles. Standards state that for commercial aircrafts, landing gear must survive 6,000 landing cycles, and for military applications, it is no more than 10,000 cycles. For landing gears, there are mainly 7 configurations as shown in figure 6. There is also a ski plane, but I cropped it. For heavy aircrafts, there are more options like multi-buggy. They have more tires. About landing gear configurations, there are some very important parameters like cost, weight, manufacturability, and taxi stability. For light aircrafts, which I am dealing with, because I am dealing with a trainer aircraft, 3-cycle configuration is very important. Since literature recommends a single wheel per strut for light aircrafts, I will use a single wheel. SEDRI compared different landing gear configurations based on parameters that I mentioned about in the previous slide. And Ceylan states that many light trainer aircrafts have 3-cycle configuration. Some of them are shown in figure 9. Where's my mouse? So here, some of them are. And scope of this study is to design a trainer aircraft's nose landing gear fork and perform a structural analysis based on hand calculations. For the structural analysis, I will use ground forces that are described in standards. And finally, I will be performing an optimization like to find out optimum sizes. And step of the study, beside literature review, are calculations of ground loads, sectional stress calculations. These are rectangular I and C cross sections, which are the most common sections for forks. Then sizing and margin of safety calculation based on von Mises yield criterion. To be able to calculate ground loads, landing gear must be located at the center of the gravity. Locations must be calculated. Due to the fuel payload, low passengers, center of gravity shifts almost all the time. Literature states that main gears must be located in 50 and 55% of the mean aerodynamic chord. So I averagely chose 52.5%. And since mean aerodynamic chord location is given in tip certificate of Hürkuş, main gears can be easily located. And also center of gravity locations are given in the tip certificate of Hürkuş. And later, I located a nose landing gear with Türkmen's parametric method. In his study, he shifts nose gear with 1.5 meters starting from the datum point, which is somewhere here. And he shifts nose gear 0.1 meter until somewhere close to main gears. And in literature, there's a restriction that nose landing gear must carry between 8 and 15% of the aircraft weight. So I calculated aft and forward center of gravity in here. And based on tip certificate and restrictions of the literature, then I applied Türkmen's parametric method. So this list is a bit long, so I will show an Excel. And yes, So I shift the nose landing gear 0.1 meters until somewhere close to main gears. And these are the minimum forces and maximum forces that applies to nose gear. And these two columns checks the validity. I mean, if it is between 8 and 15%. So there was almost 16 results, valid results. So averagely I chose 8. After all, in my study, nose landing gear is located 3 meters out of the datum point. After locating nose landing gear, I calculated ground loads. Basically, there are 4 ground load cases. These are max static, turning, towing, and supplementary conditions. Turning left and right is simple, just nose gear turns left to or right. And towing is to transfer aircraft somewhere to another place with some machines. And I have no exact definition of supplementary, but I applied to static case. And based on the standards, I calculated the loss in ground reference. Here, vertical direction is in positive z direction, and drag direction is plus x, and lateral direction is the positive through the screen. While I'm saying the standards, they are like lateral force equals to some coefficient plus static forces. I mean, the standards are like this.
Last 3 minutes.
Okay. So when I applied the coefficients, the results are given in figure 18. Since the axis orientation and my sectional axis orientation are different, I applied force translation. To do that, I used tire selection of Türkmen. In his thesis, he used this tire, and so I added a safety factor 10.2 millimeter, so it became 454.7 millimeter. So I translate the forces of the standards to my section cross-sectional, and these are the resultant force. Since these cases are independent, so we can apply the maximum values of these tables to cross-sectional template. So in this sectional stress calculations, I use rectangular I section and C section. Let me open the template. So in here, these limit loads are the ground loads based on standards. Then limit loads times safety factor is the ultimate loads. These are the inputs of geometry. Some of them are constants, I mean coefficients, like shape factor and shear factor. These are the material inputs. And so these are the shear factors, that is shear coefficients, the ratio between maximum and average shear stress. So I calculated the stresses about some critical points, and these are the von Mises calculations. So although I used the tire selection of Türkmen, I have able to design a C-sectional fork. And again, the most highest von Mises stresses are about 2.7 and 8, as you can see in here. So the missing part in this part is I have used the selection of Turkmen, but in his thesis he chose a heavier aircraft, so his tire is very high strength. About his tire selection is a bit higher than can be applied to mine selection. So in this study, there are some missing points like sizing, which is occurred to tire selection. I haven't chose my tire. And material selection, those numbers in the Excel were given to me by Mr. Taştan. So I have to choose a different material. Then I will calculate margin of safety based on one misses. So in short term, I will decide to done these missing points. And for the long-term future works, landing loads and optimization of section selection and degree can be applied. So I mean, this fork doesn't have to perpendicular to the ground. There can be some degree, and I will try to do that to optimize the forces. And these are my references. And thank you for listening. Do you have any question?
Thank you. Any questions?
Let me show from the beginning.
I've got a question, Onat.
Yes, please.
It is so nice to, I mean, you sold your results by using the Excel. It's very simple, and so it interests me so much. Thank you for your project.
Thank you.
Before all of this, so I want to ask you about just some question about. Does your results depending on the tire pressure? I wanted
Actually,
to know
no.
if, yeah.
For my project is based on static cases and for some ground loads. So tire pressure is not. I'm not considered with the tire pressure.
Okay, so is there any standard for the tire pressure for the aircrafts or something? So is there any standard for it?
Yes, the tire pressure must be below to 200 psi.
Okay then.
And
so that's why you chosen 180, I guess.
Yes, but
Okay.
that was Turkmen selection.
Okay. Okay, thank you, Onat.
You're welcome. Any other question?
This was a good question, and the pressure of the tire and the others has to be studied further in Hürjet landing gear design. This is just the beginning.
Yes, absolutely.
Yes, sure.
Yeah, no, this is a good question.
So actually, internal pressure of tire is more important when the aircraft is landing, because it dams some of the landing energy.
Right. Stiffness of the tire and the pressure and the others has to be studied further. Okay. Then İlyas Hocam, one question to Onat, and he's staying in Ankara, right? He is not coming back.
Sir, actually, I'm currently in Istanbul, but I'm still have a contact with Ankara. They have invited me to a program with includes 4 months of training and also working. And at the end of the program, I will have a exam that, as a result, I may be an employee of TAI.
This is what I meant.
Yes, yes, absolutely.
You are not coming back. You are staying there.
I'm
right?
not thinking about.
Congrats, Onat.
Thank you. Thank you.
All right.
Okay, Furkan, it's your turn now.
All right. Hello.
1 second, please, Furkan. Yes, okay.
Okay. Let me share my screen as well. Oops. All right. I think you can see my screen.
Yes, your 15 minutes starts now.
All right. So I'm Ahmet, Furkan, Çelik. First of all, greetings to all of you, all our lecturers. I'm Ahmet, Furkan, Çelik. I'm a senior mechanical engineering student in our university. And this is my graduation project presentation, which involves calculation of load distribution and the life analysis of cylindrical roller bearings with misalignment issues. It's a little long topic. So here are my contents. I will be trying to be fast in my presentation as well. The literature review part, well, we actually all know about bearings. Some know more than the other, but bearings are used everywhere in the industry, and they are very critical components because they are usually used in the powertrain systems of any vehicle or any system. That's why bearings must be considered carefully. Their loads and their life calculations should be made carefully. And I will be investigating the cylindrical roller bearings, which have different types. I will be investigating NU type of cylindrical bearing, the basic design, the basic configuration. Well, I should be investigating that because I will be investigating misalignment. And NU type of bearings are open to misalignment because they don't support axial load. And when some difference from geometry happens, or when a radial load is applied in an interesting way, there might be a misalignment, and we should be calculating those. So actually my literature depends on the physics of the subject, depends on contact stress analysis, which is a topic of continuum mechanics. This is a very broad subject. It deals with lots of parameters, as we saw in Onat's case. We can also use contact stress and Hertzian stress applications in aircraft landing gears as well on the tires. That is a topic of contact stress as well. So I will be using Hertzian equations to calculate the pressures on the contact area of the roller itself in the bearing and the bearing rings. All right, here's a little summary of Hertzian stress calculations. They are actually based off fundamental mechanics, and they are used in these analyses, and they actually have more conservative results than like finite element applications in the computational finite element applications, but they are okay for our for my study because I will be try to calculate similar results to I have seen in the papers and the literature. So I will try to develop a code which calculates these pressure distributions. To calculate the load distribution, well, here in the Hertzian approach, I have, let me change my mouse. I have a parameter here, the radial load. Well, for a point load, we can just put the F value here if we have a point load, but in our case, we have a different profile right here. This is not a point load. That's why we just can't use this formula right here to write the F or Q, because rollers also have different profiles on their contact areas. That's why I need a method to calculate the load distribution here, so I can find Q. Then I can put it in the pressure calculations. Then I can calculate the life result. Actually, this is just the broad summary of my project. And there are different methods for this. Of course, there is a slicing method, which is actually a 2D method. which I will be using. It's also a standard method and it's broadly used in the literature as well. And there are different methods. There's an alternative slicing method. There's finite element methods, of course, the computational like ANSYS programs. And there is a elastic contact theory which calculates the load distributions in 3 dimensions. All right, I really won't be talking about these too much because I will be using the slicing method in my results parts, so I will describe it there. Here is another method which we divide the contact area to different triangular shapes, or what kind of meshing we want to use. We can use all kind of meshes, and then we try to calculate the contact pressure with given formulas, or well, this is also used in literature as well. And there are different approaches to the 3D contact technique. There's a good part to this because we can skip the load calculation and we can directly calculate pressure or stress, both. That's why this is a more practical method, but it is very complicated to use because it's actually like writing a 3D finite element program by your own. That's why I tried to use the slicing method, first calculated the loads and then calculated the pressure. Here are some finite element methods, which some papers also use these as well, but these are not really feasible as well because as we know, bearings have like a different amount of rollers in them, like 10, 15 or 20, depends on the bearing configuration. That's why we are not really, it's not really feasible to apply all bearing contact stress because it will be too much computational power. So most papers just use it on one roller and then do analytical calculations after calculating the load stress. And also for fatigue life as well, there are different approaches. Well, they're not actually different approaches. There are different derivations of each other. These were the first empirical formulas, life equations found by Lundberg-Palmgren. These are empirical. They depend on some experiments. After that, other papers like Varda here developed another formula, and the ISO standard, which I'll be using, develops a formula like this. So there are different approaches, and I will be comparing them as well. This is the fatigue life method of Varda. Not going too deep in it. He has modified the empirical equation of Lundberg-Palmgren, and the equation becomes something like this. We have the parameters in the geometry as well. This is also another approach. So this is the method I will be using. This is the ISO standard for calculating bearing life, roller life, and I will be talking deeply about these equations as well. So I made a comparison of methods. I've actually presented this in my first term presentation as well. So I will not be really comparing them one by one, but I just want to say I have selected the slicing method and then calculating pressure with Hertzian equations and then finding life again with the ISO method. And I have compared this with Varda's method to actually verify my results because Varda uses a different methodology and I'm using a different methodology. That's why I think it's more healthy to compare it with a method that's really different from me, but we have the same goals. So here's my methodology. I have some inputs like radial load, moment, the bearing geometry, and etc. And then I determine the roller profile. Roller profile also changes from paper to paper, and it's critical. There are studies on roller profile optimization as well, and it's a good subject as well. And then we place our rollers. So we are trying to make a mathematical model of the bearing. We have an azimuth coordinate system, which looks something like here, the yellow one. As you see, all the rollers are placed in an angle, so I can make the calculations easier. Then the numerical study, the numerical method starts. I have an iterative method which tries to find the deformation depending on the load I give. I have an initial guess, and then the numerical method starts to find the deflection. After I find deflection, I have a stress riser function which is used, which is given in the standard. The stress riser function is a function which rises the edge stress effect in rollers, because rollers have a different loading condition in the edges of the roller. That's why we need another function to simulate this. This is a mathematical function. Then I use the Hertzian equations to find pressure, and with the given pressure and loads, I will be trying to find life. Here's my bearing geometry. These are the parameters that I have used to find my results. Here's the roller profiles I've been talking about. So as you see, this is actually a very small scale, but at the end, some rollers are bent like this. And the formula, the function of this profile, this goes on the other side as well. So the roller is something like this actually, but we can't see because it's very small. This roller profile is developed by Varda, which I'll be comparing my results, and I'm using this profile as well. And there is also a profile in the standard given. It's also a logarithmic profile, which looks something similar to this. All right, so in the physical modeling of the bearing, as I said, I placed my rollers in an azimuth coordinate system and to find my load distribution in overall in the bearing. So when I apply a radial load from here, I want to see at which angle the rollers have more load or more pressure and how it's distributed in the overall bearing. And I have also given a misalignment parameter right here. So the misalignment looks something like this. We can see it from the AA cut section view right here. So the outer ring is a little misaligned, and I will also be trying to find the misalignment angle. All right, so this is the slicing method in the ISO, where you actually just divide the contact area into a number of laminas. And then you use fundamental deflection equations like this. So this actually becomes something like F equals K times X. So this is actually like a spring rate formula, which I use in all the laminas one by one. And then I just sum them up after finding all the loads in each individual lamina. I sum them up to find the overall load. And then I find the deflection from there with a numerical method. As I see,
minutes.
Okay. As you see here, this is the static equilibrium equations for moment and load. So the equations actually become the radial load is actually equal to spring rate times the total deflection. The tricky part here is to find the total deflection after dividing the roller profile to a certain number of laminas. The contact pressure calculation method is basically the Hertzian equations. I just needed to find the Q here from the previous slicing method. So I just insert Q here, and I have the formulas for stress and the contact area, and I can find maximum stress or the pressure distribution, whatever I want. And here is the stress riser function, which I use to simulate the roller edge stresses. This is the bearing properties of the Varda's roller, which I have selected as a reference to me as well. Here are the numbers for the rollers. All right, so this is actually what I was describing at 12.2 kilonewtons. I have a load distribution like this. These are all the loads in each lamina. So 1 to 100, I've divided the profile to 100 laminas. And all laminas have their each loading. And then I just need to sum them up to find the total load on the roller. And I have some comparisons here at different radial loads. And this is the load distribution on each lamina of each roller. So 16 rollers in my bearing, and I have 1, 2, 3, 4, and another one. It's very small. You can see it 5. And so, as the bearing is symmetrical, I have actually 10 rollers which are loaded like this. So roller 1 and roller 16. Right here is roller 1, roller 16, and roller 15 is here. So roller 2 is actually the same as roller 16 because the bearing is symmetrical, but we can't see it here because they overlap. And here is my bearing and the rollers on the bearing, I have distributed the load. So this is the total load. In each roller, I have a total load like this at, again, 12.2 kilonewtons. And I have the results here. As you can see, the results are symmetrical. So the second roller and the 16th roller, they have the same load. And it's also symmetrical here as well, because this is an azimuth plot, a polar plot. And I have made it in other radial loads as well. So to create misalignment, I'm not inputting the misalignment angle, but I'm inputting the moment. So I'm inputting a moment to the code, and this moment induces actually a misalignment angle. So they have a relation with each other. And here is my input moments at different radial loads, and the misalignment angle, as you can see, climbs as the moment increases and the radial load decreases. So at lower radial loads, moments affect the misalignment angle faster. So we have it climbs faster, as you can see. All right, the load calculation with misalignment. I'm just going to go fast with these. As you can see, this is only 1 arc minute misaligned case, and this is 4 arc minute misaligned case at 12.2 kilonewtons. You can see the load distribution changes, but actually the total load doesn't change. Well, it does change, but it's like 2 newtons in 3000 newtons, so it's negligible. So we are not changing the total load, but we are changing the load distribution. So actually the material becomes more sunk, and we are actually, right here you can see, changing the pressure distribution and the maximum pressure. So this is actually a very critical result of the project. The total load doesn't change, but we are changing the peak pressure, which is important because in fatigue life calculations, we are using the peak pressure, which I will be using, showing here. So these are the methodology for fatigue life. And here, these P values, these are maximum pressure on the roller and the inner and outer raceways. So it's important to see that misalignment changes these values and also life. So as you can see, at higher radial loads, we have a decreasing life. This is a basic result. And higher misalignment angles, we have a decreasing life as well. So yeah, this is also a result of the project. And I have some verifications. These are my error rates in the project at different radial loads and at all the rollers. This is a comparison. So as you can see, it's very similar with Varda's methodology. And also, again, for the pressure as well, this is a graph from Varda, and this is a graph from my study. I go up the 4 arc minutes because the standard states that. So we take this graph as a reference. As you can see, I'm really close to 1500, and it's really close to 1500 too. And also, here are the errors for this graph. It's very small. So I think my code, it's here as well. It was in a good agreement with the literature, and I developed a GUI for calculating these. These are sold by some companies, so this can actually be developed to become a commercial program because there are like Schaeffler sells these, and there is a company named Messis, and they're really expensive. And maybe this can be developed and become more sensitive and more reliable, and maybe it can become a commercial product in the future. And these are my future works and references. Thank you for listening to me.
Thank you. Any questions?
Yeah, I can stop sharing.
Any comments? Okay, then apparently this concludes our presentations today. Thanks for attendance.
Thank you as well, our lecturers. It's nice to see you all.
Furkan,
Absolutely, thank you.
Congratulations.
Tamam.
You are our
Thank you.
first graduates.
Bu gençlerin 3'ü de mezun oluyor değil mi şimdi Temmuz'da?
Evet.
Peki, hayırlı olsunlar. Bunlar makine bölümünün ilk mezunları.
Evet hocam.
Evet.
Evet. Furkan, staj nasıl gidiyor?
Hocam ben iş teklifini
Ben
aldım.
kaydı durdurayım bu arada.
Nasıl?
Hocam kaydı durdu.